Okay, so I'm David Fouhey, this is Daniel Maturana, and Jacob Walker, and our project is semantic segmentation with discriminative mid-level patches. So the goal of our project is to take an input image such as the one on the left, and then to produce for every single pixel in the image a semantic label.
So our project is motivated by recent work in unsupervised feature extraction and computer vision. So what you see above are clusters in image gradient space. They might represent things like toilet bowls, portraits on a wall, legs of furniture. And these clusters tend to represent things that are almost semantic in nature instead of simple, stupid things like lines or right angles. And this is different from just, traditional clustering methods like k-means or such. With this method, you can get much higher level features.
Okay, so, and the cool thing with these features, because they're higher level, they actually induce meaningful correspondence when you detect them in multiple images. So if we have this green patch over here with detection in multiple image, it's not just that there's a line there, but it's actually that there's something like a floor meeting a larger object, or for example, a floor meeting a wall. And so when we repeatedly detect these features in a new image, we can actually say something meaningful about the correspondence between those parts of the image. And so we take advantage of this to define a new kernel based on these features, where the total kernel is a sum of kernels induced by pairs of these detections. And so we plug this kernel into a Gaussian process classification framework, although we could also plug into basically anything else. And we use a variety of approximation methods to actually get it to run at the scale that we need on our data set. And we show good results, which we'll show in a bit.
We also developed another approach which is designed to alleviate one of the shortcomings of these discriminative mid-level patches, which is the fact that since they are extracted in an unsupervised way, they're not always completely semantically consistent, especially when they're overlapping. So when you just aggregate the predictions of these patches, you get noisy predictions, as you can see in the leftmost example image there. To fix that, we used an MRF-based approach, in which we have a unary potential that encodes a spatial prior for each patch, and more importantly, a binary potential, which penalizes conflicts amongst the overlapping patches. So for some reason, the PDF didn't render well here, but what you should see there is that these two patches are predicting different labels on the x's. So you get a cost there for these overlapping and conflicting labels. And this turns out to be equivalent actually to a pixel-wise purity function which we exploit to minimize this energy function for the MRF efficiently. And as you can see, the net effect is that as the energy is minimized, the predictions, the pixel-wise predictions are cleaner. So to see how all this works, we used the NYU V2 dataset, which is released last year, which consists about 1,400 labeled indoor images, it's quite a challenging dataset because of clutter and noisy images. And we also implemented a more standard bag of words and support vector machine kind of approach with 3 different kernels. And we held the features constant because we wanted to get a feeling for the machine learning part of the pipeline, not feature part. And as you can see, all these VM approaches fared more or less the same, whereas our 2 approaches were significantly better, and the GP comes ahead by a small margin. And you also have here some example qualitative results, and you can see how the GP and MRF approaches are better than the other 3. I mean, than the other 2, and you also have the ground truth there for comparison.